Well, hi there. It's your old pal, Mr. Cook, and we are going to work through this Unit 3 practice test, Part 1. We're not allowed to use a calculator, so yeah, let's see what we can answer without the use of our handy-dandy calculator. So it says that the figure on the right shows the graph of the actual function, f of x. Find the following and then approximate the coordinates to the nearest half. Okay, so the nearest half of a point. So we first need to find out critical values or critical points for the x value. So a critical point is when the derivative of the graph is equal to 0, or if the derivative of the graph for some value of x does not exist. Those are critical numbers when we see that. So how does that look on a graph? Well, the derivative being 0 will look like it's going to be a maximum or a minimum point. It's basically where the graph goes from increasing to decreasing or decreasing to increasing. So those would be critical values. Okay, so to find those critical values where the derivative would be equal to 0, I just need to look for like a potential, top of the hill of the graph or the bottom of the hill of the graph. So there's the bottom of the hill, the top of the hill, the bottom of the hill, the top of the hill. Okay, so all those x values, one's right there, -1, another one at 1 there, another one at 2, another one at 3, and then another one at 5. All of those would be my critical values for x, okay, for this function. So I say x is equal to -1, 1, 2, 3, and 5. So those would be the critical numbers for that one. Now, there's also a case where you have the derivative, and it gives you some kind of situation where you have division by 0 or something weird, and you have a DNE. That's like where you have, say, a vertical asymptote through some function. That x value would be a location of a critical value, but we don't have that on this graph, so we really don't need to worry about that. We've got all the ones that we need. Okay, so then we've got the critical numbers. Now let's find the intervals where the graph is increasing or decreasing. So what does that look like on the function? On f of x, the graph of fx, increasing looks like this. It's going up and to the right. Okay, that's how increasing looks. Decreasing looks like it's going down and to the right. Okay, so if I look at the graph, I'll just color code this real quick. The parts where it's going up and to the right or increasing, that's going to be like right here. It's going up and to the right until there. And then it'll be going up and to the right over there. And then I've got another spot where it's going up and to the right, like right there. So these are all the places where the graph is going up and to the right. So those are all the ones where it's going to be, the graph is going to be increasing. So let me write up those intervals real quick. It looks like, I'm starting off on the left-hand side all the way until I get to about -1, it's going to be increasing. So that's how I'd write that up. On the x-axis, I'm like starting all the way over here, and it's increasing all the way until I get to that point right there at -1. So negative infinity for x all the way up to -1, this graph is increasing. And then it looks like I've got another interval where it's increasing, like right here. So that's on the x-axis from 1 to 2. So from 1 to 2, I'm also going to be increasing. And then it looks like my graph is increasing also, like, this little area here from, when it starts at 3 going all the way up until on the x-axis it goes to 5. So from 3 to 5, it's also going to be increasing. So if I have multiple intervals, I just put u's between them, the unions, and it groups all of the intervals together. And that's where I'd say that my x values are going to be increasing. So I just write, increasing and then write the intervals next to it. Okay, and then on the other hand, the graph is going to be decreasing when the graph goes down and to the right. So those are intervals, that look like this. So down and to the right here, down and to the right over here. And then it looks like for the whole rest of the graph, it's going to be going down and to the right as well, but just like really slowly, but still down and to the right, like forever after that. So along the x-axis, my intervals where the graph is going to be decreasing are as follows. It starts at -1 and goes all the way over to 1 on the x-axis. So I'd say -1 to 1. That's one interval where it is decreasing. And another one right here on the x-axis from 2 to 3. So from 2 to 3, it's also decreasing, that red interval. And then from 5 until forever. So the way that I write that one up is I write 5 and then infinity for that one. So then I group them all together with unions, and that's my intervals where the graph is going to be decreasing. Okay, the next stuff that we're going to learn about is, review, is the second derivative stuff. So with the second derivative, that tells me where I have concavity and also where I have these things called inflection points, which is where the graph is going to be changing concavity from concave up to concave down or concave down to concave up. So I'm going to go a little bit out of order. I hope you don't mind. But what I'm going to start with is like identifying where the graph is concave up and concave down. Okay. So I'm going to erase all this stuff. You can just rewind it if you need an explanation or the answers again. Okay, so here we go. Concave up, let's start with that. Concave up is where the graph will look like this. It'll look like kind of like a U shape, either that or that. So I just look for those spots where, it's kind of a, I don't know what you'd call that, like an L shape or a J shape. Okay, so it looks like I've got that here. See, there's that like L shape kind of, it's curved downwards, and then it looks like it's going to be concave up like right until maybe like the halfway point. Then it changes to concave down, and kind of same thing here, maybe like right there it starts to go concave up and it stays concave up until it gets maybe to right there, then it's concave down. And then it looks like there's a spot like right here where it starts to get concave down, concave up like forever, like right there. Okay. So those are all instances where the graph is going to be concave up. So I just start writing up the intervals for that. And concave up on a graph is just like kind of how it looks, okay? It has to be one of these two shapes, like the curved L or the curved J, okay? So it looks like it's concave up on the first green interval from 0 all the way until it gets to about like probably 1.5, I'd say. Because it says to round in the nearest, half point. And then I'm going to guess from like 2.5 on the x-axis all the way until it gets to about 4. That's also going to be concave up. And then for the last one, I'm going to guess that that's like 5.5. And I'm going to say that it's concave up for the whole rest of the way. So about 5.5 all the way up to infinity. It's going to be concave up. So I'd, write the unions between those intervals. And I just write concave up. Go. And then concave down is the rest of the stuff. And I want to make sure that, it looks the way that I want it to look. So concave down looks like this. It's like either an R shape like that, like a lowercase r, or it's like this shape, which I guess would be like I don't know, like a 7 or something like that. I don't know. A curved 7. I don't know. But you can see that plainly like right here. Here's like a place where it's concave down. Then here's another one where it's concave down. So that whole interval is concave down. And it's like basically all the other ones. That's where it's going to be concave down. You can see that it's got that kind of like N shape to it. It's both parts of the lowercase n, I guess you could say. And that's just going to be the remaining intervals, right? So it starts at negative infinity and goes all the way up to 0 along the x-axis. That's one interval where it's concave down. And then another one where it's concave up is going to be from 1.5 all the way up to about 2.5, it looks like. That's this one here. And then it's concave down from 4 until about like 5.5. Then it's concave up after that. So 4 to 5.5, and then concave up the rest of the way. So then we just put our little unions there and say that this is concave down now. And there's our intervals where it's concave up and concave down. Now, the reason that I did that, I did concavity first is because that'll help me to really identify where my inflection points are. So the inflection points happen when I change from concave up to concave down or concave down to concave up. So, like on my graph, it's where I change from red to green or from green to red. So like this is a point right here where it changes concavity. So I'd say that one of my inflection points is going to be at x is equal to 0. That's for sure one of them. And then it looks like, again, it changes concavity like right here, changing from green to red or concave up to concave down. And that happens at around about 1.5 by my estimate. Similarly, like we've got this point of inflection where the concavity changes, and I think that's around 2.5. And then looks like 2 more. I've got one right there where it changes concavity from concave up to concave down at 4. And then finally, like right over here, it changes concavity again at about 5.5. So all of those would be my inflection points. Okay, so there we go. Now we need to get to the relative extrema. We're going to erase all this stuff. You can always rewind a little bit if you need this stuff back on here. All right, here we go. All right, and then the last part asks us to find all of the relative maxima. And you know what? I'm going to change this up. Maxima means like this, the maximum values. I'm going to change to extrema. So extrema, if I say that, that implies that it's both the maximums and also the minimums, okay? So, I just can look around in the graph. It looks like I've got a maximum right there because it's at the top of the hill. And again, since this is the original function, f of x, I'm just like basing all of these maximum values from the function based off of, what I'm seeing in front of me. So whenever I see a bottom of the hill or a top of the hill, that'll give me all of those values that we're getting to. So the relative extrema over a small period of, x values, it looks like I've got a maximum value right there. Let me list off all my maximums, my relative maximums. Or maxima, I guess. And also my relative minima. All right, let's see where they happen. So the maxima happen at the top of the hill, and the minima happen at the bottom of the hill. All right, so it looks like I've got maximum values at -1, at 2, and then also at 5. And then I've got relative minima at the bottom of the hill at 1 and 3. And those are all of my relative extrema. I went a little bit above and beyond part E, but whatever, I think it's good enough. Okay, we've been doing this for a couple minutes. I think that's a good place to stop. So hopefully this video helped you out. We'll go on to the next one and we'll do the derivative graph. Hope to see you there. Bye-bye.